Hello scholars, welcome. Mr. Hinkle here. We're talking about plate tectonics and in specific plate tectonic boundaries. And in this lecture, we're looking at transform boundaries. So that is our objective. Explain transform plate tectonic boundaries with examples. Let's go. So, because I love saying it, plate tectonics is the unifying model of geology that states that the surface of the Earth is covered with large rigid bodies of rock called tectonic plates. And they move around relative to one another, and where they meet is a plate tectonic boundary, and there are specific interactions. We have divergent, where two plates move away from each other. We have convergent, where two plates move towards each other. And we have transform boundaries, where two plates slide past one another. And so that is this. A transform boundary is where two lithospheric plates, Earth's crust, continental or oceanic, move by one another. These are also called strike-slip faults. In the world of faults, we have normal faults, we have reverse faults, we have thrust faults, we have strike-slip faults. So this is a large type of strike-slip fault, but it is specific to plate tectonic boundaries. We have the plates moving in opposite directions, and the movement is horizontal, so there's no vertical displacement. It's all horizontal movement. Now, the way that we classify these is right lateral or left lateral. So we're looking at dextral versus sinistral. And if we look at the plan view overhead, let's say here's a block of rock. If the block moves this way and I'm here, one happy geologist, yay! Okay, so I'm here and I want to look at the block on the opposite wall. Now, I'm here and I'm looking at the block on the opposite side. What way is it moving? Left? Great. What if I'm over here now? And I look at the block on the opposite side. What way is it moving? Left? So we would say this is a left lateral or sinistral movement. Now let's go and do this exercise again. Here is the fault, the transform faults. Here is the faults. Now it's going to move this way or this way. And let's put us here. Yay! Okay, so now my eyes are looking at the block on the opposite side of the fault. And what way is it moving? To the right. Put me over here. What way is it moving? Also to the right. So here we have a right lateral or a dextral transform faults. Physical geology is all about looking at the physical characteristics of our Earth. What do we see with our eyes? What can we interpret with our data to observe how our Earth functions? And transform faults are no different. So we have two groups of transform faults. We have very large tectonic boundaries like the San Andreas fault, and then we also have transform faults associated at mid-ocean ridges. The mid-ocean ridge system spans the Earth. 65,000 kilometers of underwater volcanoes. That's awesome. And they line, they permeate, they transcend the oceans, the center of the oceans, like the seams of a baseball. But they're not actually flat. We often say a transform fault, or I'm sorry, a divergent boundary is a linear feature. That's the word I'm looking for. We say they are linear, but they're not actually linear. They have a series of steps to the left and to the right. So here's our divergent boundary. Divergent, moving away, like so, like so, like so, like so. Now, we are going to connect the divergent portions of the mid-ocean ridge with transform faults. Need a little bit more length on that one. And a little bit more. There we go. Great. So this one is moving this way, and this plate is moving that way. Same here. We've got motion that way and that way. This one goes the opposite way. So on and so forth. So this is the mid-ocean ridge that is a divergent plate boundary. But within that divergent plate boundary, we have transform faults that accommodate the lateral motion associated with the divergence. Here is a good example. We've got the mid-Atlantic ridge between South America and Africa. We zoom in here and we say, yes, okay, so here's divergent and here's divergent, but a transform fault connects the segments of the mid-ocean ridge. So when we're thinking about divergent plate boundaries, they are intricately related. It's like we want to zoom out and think about things from a simplistic point of view, but once we understand the fundamental nature of how something works, we can start to get into the complexities, into the nuances, and this is what we get with plate tectonic boundaries. We get to start to understand the complexity and the nuances of how mid-ocean ridges actually are built, their structure, and their processes. Transform faults between plates. So here's mid-ocean ridge. Look at that. A little bit of divergent, 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 divergent. Look at all these transform boundaries. A triple junction here between the North American, the Pacific, and the Cocos Plate. Our beloved, I'm in Fresno, California, our beloved San Andreas Fault. Look at this big bend. I'm going to talk about that here in a second. A big bend in the San Andreas Fault, and then nice and long. The San Andreas Fault is, and I have a slide on it coming up, but it's responsible for the big earthquakes in our major metropolitan areas because this thing builds tension, it builds tension, it builds tension, and then ka-chunk, it releases that tension through displacement of the rock that releases energy via seismic waves that shake the surface of the earth, causing earthquake destruction. If you look at it from overhead, the San Andreas Fault is a big gouge in the earth. It's big. It's roughly 1,200 kilometers, and it forms part of the tectonic boundary between the North American plate and the Pacific plate. If you're standing here, this plate is moving this way. If you're standing here, this plate is moving this way. So that gives us right or left lateral. You guessed it, right lateral. The San Andreas Fault is a right lateral. Right, I'm here. And I'm looking at the other side, and it's moving to my right. San Andreas Fault is a right lateral strike slip fault or a right lateral transform fault. The Alpine faults bound some mountains. These are responsible for the big earthquakes in the South Island of New Zealand. This is the South Island of New Zealand, the North Island of New Zealand. You've got a convergent boundary to the north, you've got a convergent boundary to the south, and they're connected between this large transform fault known as the Alpine Fault. It's also pretty big, about 370 miles, forms the boundary between the Pacific Plate and the Australian Plate. So transform faults help connect. It's kind of like Earth's way, because if Earth was flat and plate tectonics was happening and a divergent boundary was developed, it would just be perfectly linear and push it and probably push the mountains off the edge of the flat Earth. But this doesn't happen. Earth is a sphere, and since it's a sphere, these straight lines of mid-ocean ridges actually wrap and warp, and there's places in between that need to connect, and this is what transform boundaries can do. They help connect. evidence that we see. The pinnacles are really cool rocks in Central California, located right along the San Andreas Fault. Well, these rocks are the exact rocks. In fact, it's part of the Ninoc volcano that was split. The Ninoc volcano erupted right on the San Andreas Fault. The San Andreas Fault split it in two and then carried it 195 miles to the northwest. It's on the west side of the San Andreas Fault. The Ninoc volcano is on the east side, and then this is a right lateral, and we see 23 million years ago this volcano erupted, and then it split along the San Andreas Fault, and it has been carried to its current location. So it's cool when there are geologic discoveries like this that help us to provide supportive evidence for these ideas that we have, like continents move across the surface of the Earth. That's called plate tectonics. Now, we've got transpression and transtension. Remember that big bend that I was talking about? Here it is, a restraining bend. This is transpression. This is happening in the San Andreas Fault, and this is responsible. It's actually turned the coastline right along Ventura and Santa Barbara. It's turned the coastline so it faces north-south, where the rest of the coastline faces east-west. Created the San Andreas Mountains behind it, and this is how transform faults can be contributors to landscape development. Landscapes evolve over time due to the active tectonics that are being applied to them. Active tectonics is what's happening at plate tectonic boundaries. So we have a restraining bend, cool geology there in Southern California. We also have a releasing bend. These create different types of features, mountains and or lakes from the space that opens up in Earth's crust. 1906, huge earthquake in San Francisco. The Great Quake of 1906, but when it happened, they called it the Great Fire because seismology was a very young science, and plate tectonics hadn't even developed yet. Nobody knew that continents were moving across the Earth. Alfred Wegener in 1912 proposed continental drift. People didn't accept his ideas for another 40 years. So in 1906, when this fence gets offset in Marin County, people are just going, I don't know exactly what the heck happened there, but this fence was offset at the same time that an earthquake occurred, a large earthquake. Now we know this offset is right along the San Andreas Fault, and when there is movement on the fault, the energy released creates an earthquake. Earthquakes are cool, they're powerful, they are a natural disaster, and they occur every time there's movement. Every day, there's an earthquake happening right now. Every day there are thousands of little earthquakes happening. Little, so small that we might not perceive them, but our technology picks them up. And we use that to understand where our plate tectonic boundaries are. This is just an image and a graphic. We use that to understand where our plate tectonic boundaries are. We can trace the outlines of the tectonic plates by mapping the distribution of the earthquakes that occur on Earth every single day. So transform boundaries are a key piece of the puzzle for understanding plate tectonics. There's three types of boundaries: divergent, convergent, and transform, and they all work together to create and shape the surface of our Earth. Thank you so much. I'll see you in the next one.